So we've all seen big O before, but you may have run across similar notations like big omega, big theta, little o, and little omega. Now if you're like me, you don't actually see these that often, so you've forgotten about them. And that's okay. What we're going to do in this video is start with a quick review of the definition of big O. Then, from that definition, we'll discover why we need each of these other notations, what exactly each one means, and how they relate to each other. Let's get started. So here's the mathematical definition of big O. Now this video doesn't focus on big O, so we're going to run through quickly what each part of this definition really means, really stands for. Let's look at f of n first. F of n is kind of a stand-in for how many operations my algorithm runs, or how much space it uses. And it's a function of n is just how long the input is. G of n is a function that goes inside the parentheses for big O when I write it down, as you can see. G of n is usually something like n log n log n squared, maybe for something slower, 2 to the n, and so on. You can see from the definition that f of n is going to be less than or equal to g of n times some c. Now c is a constant that we get to choose to make the definition work. I also get to choose n sub 0, also called n naught, that's n-a-u-g-h-t, that means 0, n naught. And n naught is the value above which the inequality has to hold. So g of n is what we'd call an upper bound. You can see that here because f of n has to be less than or equal to c times g of n. But what if I want to go the other way with f of n and g of n? What if I want g of n to be a lower bound on f of n? What would that look like? So we can just go into the definition and quickly swap these two around. Very nice, very neat there. And actually, that's the definition of big omega. That's it. Big omega is a lower bound of some function. Now, what does that mean to us? What does it mean to be a lower bound on something? Remember that when we're looking at algorithms, we usually like low numbers, and because we like low numbers for less time, less space used, we like functions that grow slowly. So a lower bound is kind of like saying, we're not going to do better than that. Okay, maybe we can get to that level, but we're not going to do better than that lower bound for this algorithm. So an example of that would be on comparison-based sorts. We have a lower bound, we have a big omega of n log n. And that's just saying for quicksort, which you can see here, or for any other comparison-based sort like merge sort, or anything anyone would ever think up, if it's a comparison-based sort, we're not going to do better than n log n. Now maybe for radix sort or some other sort that doesn't use comparisons, you could do better, but they've proven that you're never going to beat this for comparison-based sorts. You can try looking, you'll never find a better comparison sort than n log n. That's what big omega is really saying. Now going back to the definition of big omega, let's take an example algorithm and see if we can make it fit the definition. So for our example algorithm, we're going to use insertion sort. It's a simple, accessible example. Here's a quick visual of what insertion sort looks like. An insertion sort needs this many swaps and comparisons in the worst case. There's a link in the description if you want to know how I got that. And so as you can see, we're calling this number of swaps and comparisons f of n. And you'll also see people use t of n, whatever, it doesn't really matter which specific letter we use. And let's apply this definition of big omega to our function f of n here. Now if you look at the definition, you'll see that we want g of n times a constant to be less than or equal to f of n. And so we're going to choose g of n to be something really small, much smaller than our f of n. Let's go ahead and say g of n is equal to n. And we can also choose c to be something small. Let's choose c to be 0.1. And n naught to be, let's just say 10. Now if we plug all these in, we can see if the inequality holds. And it does, right? And we can plug in something slightly bigger just to double check. and it still holds with room to spare. So insertion sort is bounded from below by g of n equals n. But why can't we just choose something much lower, something really low? What would the lowest thing we can choose be? It would be g of n equals 1. Just 1. It's always going to be 1 no matter how big n is. And this seems like a weird choice, right? But actually I can still make the definition work. I can choose n naught to be 2, the inequality holds, and the definition's still going to work no matter how big I make n, because you can clearly see g of n will just never be bigger. It'll always be 1, it'll always be less than, and so we can also write that f of n is omega of 1, or constant time. Now recall that f of n represents the number of swaps and comparisons in the worst case for insertion sort. So I've got two different big omegas for one algorithm. Now does that seem okay to you? Does that seem right to you? Think about that. Pause the video and think about that if you'd like. And in fact, according to the textbook definition, these are both perfectly correct. We can have multiple different big omegas when analyzing one algorithm. But could we have multiple different big O's? So let's clear that off. I'll put the definition of big O back up, and we'll see if we could do the same thing with big O. And notice the key difference between the definitions, again, is that with big O, I want f of n to be less than or equal to c of n times g of n. So I'm going to choose g of n to be something I know will be bigger. I'm going to choose n cubed. Now, some of you are thinking, no, you're supposed to choose n squared there. Well, I'm not going to. I'm going to choose n cubed, and the definition's still going to work. So I'm going to pick c equals 1 and n naught equals 1. And let's check it. You can see it holds. We can plug in something bigger just to be sure. Of course, it still holds. So I can say that this function f of n representing insertion sort has an upper bound of n cubed. But if we're saying upper bounds and we're just trying to make the definition work, why stop at n cubed? Why not go for something much bigger? How about n to the 10, or 2 to the n, or n to the n, or even something bigger than that? I don't know what that would be. You can tell me in the comments. So why don't we just use these? Will the definitions still work with these? And I'm not going to run through the math. You can do that yourself if you want, but these will all hold. We can also say that insertion sort, represented by f of n, is O of n to the 10, O of 2 to the n, O of n to the n, and so on. And this seems kind of dumb, right? Is this actually a useful way to talk about the algorithm? And the answer is no. It's not really useful to talk about it like this. If you think about it, what we kind of want is we want to choose the lowest upper bound that we can, the smallest upper bound. But that sounds a little confusing, so let's just change the terminology, and let's say we want a tight bound, But what exactly would that mean? We're looking at mathematical definitions here, so what would it mean to be a tight bound? What would it mean to kind of be the lowest upper bound? Well, we can look at that. I've put back up the definitions of big omega and big O. And have a close look again at the inequalities. You will see in big O, I changed the name of the constant from C to D. Now, where do you think I'm going with this? See if you can guess. Where I'm going with this is that I'm going to combine these two inequalities into one big inequality. And we're going to have a close look at this and really think about what it means. What does this inequality really tell us about the relationship between g of n and f of n? Here's a graph that will help you see. You can kind of see that g of n on the graph almost surrounds f of n. C times g of n comes in from the bottom. D times g of n comes in from the top. They kind of surround it. And if I adjust the constants c and d, I can make it squeeze in on f of n. And that's what we mean by a tight bound. You can kind of visualize it in this way. So this notion of a tight bound and this inequality we've created, this is really the concept of big theta in a nutshell. And here's the formal definition of big theta. Big theta is special because it's defined to be a tight bound. So let's see how this definition fits with our example of insertion sort. You'll remember that f of n represents the number of swaps and comparisons in the worst case for insertion sort. So what we're going to need to do here is find g of n, c, d, and n naught to make the definition work. We're going to choose g of n first. You kind of have to choose g of n first because you can't really know if the other ones are correct unless you already have a g of n. And you'll recall for big omega, we kind of had multiple options for our lower bound. For big O, we had multiple options for our upper bound. Are we going to have multiple options here? No. There's only like one good choice here. And so what we want to choose is we want to look at our function f of n and choose the dominant term. Now what would that be? For a polynomial, this is super easy. Just look at the exponents, grab the biggest exponent, and set your g of n to be n raised to that exponent. So for us, it'll just be g of n equals n squared. Now for c and d, which one has to be bigger? Yeah, d is going to be bigger. So we're going to choose numbers, easy numbers, that hopefully will make our definition work. We're going to choose c equals 0.1, we'll say d equals 10, and let's just choose n naught to be 10 as well. Let's see if these numbers work. It does. The inequality holds for n equals n naught, and we can check 11 and 12 as well, just to be sure. You can see the inequality is still holding, and the gaps are getting bigger, so it should continue to hold. Therefore, we can say that insertion sort, represented by f of n, is big theta of n squared. Now, that's great. Can we also say that it is big theta of n or big theta of n cubed? No, that's not going to work. You're never going to choose numbers that make this inequality work for g of n equals n or n cubed or plenty of other functions. But you could actually still say that f of n is O of n squared. You could also say it's big omega of n squared. And that shouldn't be surprising, right, given how we derived the inequality. And the thing is, this is more than just a nice way to present the definition. You can actually define big theta exactly in this way. The double arrow here is just logic notation that says the left means the same thing as the right. Now, something to be aware of while we're here is that the definitions I've given you for big O and big theta are what people use in a course or in an academic context. And the thing is, outside of academia, outside of like university and formal courses, people use big O to mean a tight bound. They kind of just assume if you give a big O time that you're talking about a tight bound. So if you go into an interview, for example, and you tell them that insertion sort is O of n to the n, technically, according to the textbook definition, you're right, but they may think you have no clue what you're talking about, right? So I'm not going to say that the people in these interviews, the people using big O this way are wrong. That's just how they use it. That is kind of a more useful way to talk about it. But do be aware that there's this difference between how people talk about it like in the workplace versus how people talk about it in courses. I'm going more with the textbook definitions here in this video, as you can see. And so that's big omega and big theta. We've got the two little ones left, little o and little omega. And these are still a bit less common than the others, so I'm going to run through them a bit more quickly. What little o is a loose upper bound. That means it's an upper bound that cannot be tight. Big O can be loose or tight as an upper bound. Little o cannot be a tight bound. And so what does that mean exactly? We're going to look at this graph. F of n is just going to be n, and our upper bound will be n squared times some constant. Now, what if I make the constant multiplier for n squared really small? it almost looks like this n squared times a constant is not an upper bound on n. But actually, if we zoom out, it still is. Well, can't we just make the constant even smaller? Yes, but if we zoom out, we can still see that there's this point at which n squared will overtake it. And so that's really the core idea of this loose upper bound of little o. So if we use n naught to mean the point at which the upper bound overtakes f of n, we get this definition. Now this appears similar to the big O definition, but there's a few small changes here that actually make a huge difference. Notice for C it now says for any, not there exists. What this means is that we don't get to choose C in the way we were doing earlier. Here C is kind of what we were doing on the graph. No matter how small you make it, there will be some n naught beyond which g of n overtakes f of n. And those n naughts will be different for each constant, as you can see. As I said, this is really just a formalization of what we were doing on the graph. Another key difference in this definition is you'll notice on the bottom line, we now have a strict less than c times g of n, whereas before we had less than or equal to. Now we can get the definition of little omega from the definition of little o in exactly the same way we got the definition of big omega from the definition of big O. So we'll just do this swap in the inequality. And here's the definition of little omega. Now that curly W thing at the front is actually what a lowercase omega looks like. Why does it look like that? Why doesn't it look like a small version of capital Omega? I really don't know. Sorry. And so we've got little o and little omega here. And what do these mean to us? I said these are loose bounds. What does it mean to be a loose upper bound or a loose lower bound? Well, for little o, the loose upper bound, it's kind of saying we'll never get that bad. Remember, we don't generally like large numbers and quickly growing functions here, so little o is saying it'll never get that bad. Whereas little omega is almost like saying we'll never do that good. So that's kind of an intuitive sense of what little o and little omega mean. So I hope you understood and enjoyed my explanations of big omega, big theta, little o, and little omega. I certainly enjoyed making the animations for this, and I also enjoy teaching. So if you're looking for a guide, a mentor, a companion on your road to learning to code and learning computer science, go ahead and check out my website, CoachSlateTutoring.com, and we'll see if I can help you reach your coding goals. I want to thank you for watching, and have a wonderful day.